Scott and Greta, if you know her, agreed on a strategic alliance. Scott is a professor at UT Austin. He could be director of the National Science Foundation. He could be White House science advisor. Now the problem with that one is that there has to be someone in the White House to advise.
Maybe you get while you're ahead, Greg.
And see, now the other problem with any of those suggestions is that Scott has decided on his own what's really important, and that is to prove Gil-Khalai wrong. And that's why we have the pleasure of having him, the privilege of having him today to talk about random circuit sampling. So,
Thank you, Greg, for that a unique introduction. So yeah, it is great to be here as always, and I would indeed much rather be here than at Davos, having experienced them both. And I did pick up a cold there, and I apologize if I lose my voice, but fortunately it's a small room. Now I do feel a little sheepish because Adam already did such a spectacular job this morning at sort of explaining the basic theory of quantum supremacy experiments that I'm sort of reduced to providing some comic relief to go afterward. But no, it's actually very useful for me because I will build directly on what he talked about. And so what I think I'll do is I'll pick up literally right where he left off, talking about the actual test that Google applied in its recent experiment, this linear cross-entropy benchmark, and what do we know about the classical hardness of spoofing that benchmark? Long story short, not as much as we would like, although not completely nothing either. And then what I want to do is just sort of tell you what are some of my favorite open problems and future research directions about quantum supremacy, because I think that this is not like a one shot. Google did it and then we're all finished, right? We are now at the very beginning of an era of 50 to, let's say, 200 or 300 qubit noisy quantum computers that look like they will mostly be good for various sampling tasks. And so, it would behoove us to figure out, well, what sampling tasks are out there. Are there any that are actually useful to anyone that people care about? How sure are we that they're hard for classical computers to simulate? How do we verify their results? Okay, and I'm going to try to convince you in this talk that even at the purely theoretical level, there is more open than closed about all of those questions. Okay, and just to show you what some of my personal favorite directions are. So, okay, so let's go back to the basic setting of random circuit sampling that Adam talked about, and we have a verifier that generates quantum circuits from some probability distribution. In the case of Google's experiment, these are two-dimensional, nearest neighbor circuits on a grid, with some particular gate set, which happens to be computationally universal, but of course we could attach numbers to it. In their experiment, n, the number of qubits, was 53. The number of layers of gates in their hardest circuits that they were able to do and still extract the signal was about 20, depth of 20. So you're talking about on the order of 1,000 gates maybe. And so they generate this circuit randomly. Now you might, the question came up this morning, you might already be worried that in the experiment that's been done, Google was both the verifier and the prover. That could certainly be addressed in the future, and that's just like a one tiny example of the many things that remain to be done here. Okay, but let's just trust for now that they did generate a circuit in the way that they said. Then basically what happens is that circuit is sent over to the quantum computer, or more literally a classical computer programs in the circuit by control wires that go into the dilution refrigerator, loads the circuit onto it. This is my stylized quantum computer. It's forgive my poor artwork. Then the quantum computer is challenged to quickly generate samples from the output probability distribution corresponding to that circuit. Okay, and this is some distribution over n-bit strings, in which is not a uniform distribution. Some of the strings are likelier than others, even though all of them in general are exponentially unlikely, right? But some have probability like 2 over 2 to the n, others only 1 over 2 to the n or less, and those little non-uniformities are precisely what we are looking for. Okay, the whole point of the experiment is going to be to check whether the samples that are generated are preferentially clustered among the ones that were predicted to have the higher probabilities. Okay, the conjecture being that task, generating samples like that, is something that should be hard for a classical computer, and we will of course have to come back to the evidence for that. Okay, so as Adam discussed, the test that Google ended up applying is one of the simplest ones that you could possibly write down. They call it the linear XEB, linear cross-entropy benchmark, all you do with this test is that you take all of the samples that were generated by the quantum computer. So each of these S1, S2, and so forth is each an n-bit string. In this case, a 53-bit string. Okay, K is just the number of samples. So just to give you a sense, K is going to be tiny compared to 2 to the n. Okay, so you will see a number of samples that is sort of not nearly enough to fully characterize this distribution. We simply don't have enough time for that. But the number of samples does have to be large enough that you can do valid statistics on it. Okay, and so K, the number of samples, will be partly set by the amount of noise in the device. And good rule of thumb is that if the fidelity of the quantum computer is epsilon, so meaning, if we're sampling from, let's say, epsilon times the distribution that we really want, plus 1 minus epsilon times the uniform distribution, or something like that, then the number of samples that we're going to want is going to scale roughly like 1 over epsilon squared. Okay, and that's just a basic matter of statistics that, in order for us to even detect information theoretically that this signal is there, we're going to need this many samples. And I should add, by the way, that the actual distribution, is not going to be exactly like this, or we certainly don't know it to be like this. And in our hardness arguments, we will not be relying on the assumption that the distribution has this form. This is just a heuristic. Okay, so in the case of Google's experiment, epsilon is meaning the fidelity of the device was about 0.002, right? About 1 in 500, and so the K that they took was several million. Okay. That sounds like a lot, but the good news is that once the circuit is loaded onto the chip, then each sample, each S sub I, can be taken in about 40 microseconds.
What does it mean, load the circuit onto the chip?
It means, you know, to sort of initialize the circuit, you know, get the chip ready to apply this circuit over and over again. Okay, so there's some startup cost to doing that, which is, you know, maybe like a, you know, I don't know, 100th or a 10th of a second or something like that. Okay, but then once it's loaded, yeah, that once it's preloaded, then each of these samples is only about 40 microseconds.
And you're making an assumption that they're independent?
Well, we are not assuming that they are independent. You know, in the sort of honest case, we are hoping that they're independent. But even if they are not entirely independent, you know, our hardness arguments will not depend on the assumption that they were.
Right? More of a physics question than what you're talking about. I wasn't.
Yeah.
Anything would be loaded onto the chip itself, but it could be in some sense loaded into the equipment. Right?
Yeah, yeah. It's loaded into the control system. Yeah, yeah. Okay. So yeah, and you know, and the very fact that I am, you know, quoting you these numbers, I think, is like a sign of how our field has evolved. You know, and that, you know, I think if I were giving this talk 10 years ago, I would have said, well, you know, each sample is, you know, is O of 1, or you know, rather, you know, O of D, or D is the depth, and just left it there. Okay, but
like everybody said, it's Kitty Hawk.
oh yeah, okay. So so now with the linear cross-entropy benchmark, what you're going to do is you're going to just, with your classical computer, calculate the sort of ideal probability for each of the samples S sub I that you saw, and then you're just going to sum them all up, and we're going to consider the test to have accepted, you know, we're going to consider the quantum computer to have passed the test, if and only if this sum exceeds some threshold. Okay, so you know, intuitively, the better the experiment, the larger should be this sum, right? Because we should be, you know, preferentially be finding the outputs that we're supposed to have larger probabilities, right? That's kind of what the quantum computer is supposed to do. You know, we can now just think about, well, what values of this sum would we expect? And so let's first consider, well, if we just had a classical computer that was just generating the S sub i's uniformly at random, you know, just completely ignoring the circuit C, then what value would we get? Well, you know, each probability in expectation is, of course, 2 to the minus n. You know, some are a little larger, some a little smaller. But if I just add up k random ones, then I would expect to get about k over 2 to the n here, which means I'm going to call that a value of b equals 1. Okay, now we can next ask, what if we had an ideal quantum computer with no noise whatsoever? And then this is just simply a calculation that you can do, where you use the fact that if I take a random sequence of gates, random circuit, so you know, if it's a small random circuit, it will not produce a Haar random state, because you know, there aren't nearly enough degrees of freedom in a small circuit to do that. But it will produce a state that for most purposes behaves as if it were a Haar random state. Okay, and in a few cases, this can even now be analytically proven. Adam mentioned the results of Aram Harrow and Saeed Merabban, for example. And even in the cases where it hasn't been proven, it is known to be true by means of MATLAB. And so assuming that the amplitudes are, you know, like independent complex Gaussian variables, which is, you know, what they will be in a sort of fully scrambled, you know, scrambled up, random looking quantum state. Now the key point is that, well, you know, if I draw a bunch of complex Gaussians of mean 0, well, you know, they'll have slightly different distances from the origin. Some will be a little larger and others smaller in magnitude. And there's a beautiful mathematical fact that if you take the squared absolute value of just a complex Gaussian in order to get a probability, then this gives you precisely an exponentially distributed random variable. Okay, so the probabilities, you know, in this distribution D, or we could call it D sub C, are going to be exponentially distributed random variables, right? They have a mean of 2 to the minus n, but they can be larger or smaller. Okay, so like that. And by the way, this is only true of amplitudes or complex numbers. If they were reals, if they were quaternions, it would not work out exactly this way. Okay, so but now using the fact that the probabilities are sort of exponentially distributed, one can calculate. You just do an integral for sort of what is the expectation of this sum if I actually sampled the S sub i's from DC, if I sampled them with an ideal quantum computer. And the answer turns out to be that I would achieve this inequality with b equal to 2. Okay, so the quantum value is sort of exactly twice the classical value, if you like, okay, or the random sampling value. So now, what I really like about this is that in some sense we have a computational complexity analog of the Bell inequality, right? So the Bell inequality said here's an experiment you can do. Here is some inequality that we expect that in any classical picture of the world will be satisfied, and then here is the prediction of quantum mechanics, and it violates that inequality, right, by some constant amount. Okay, and now when we do the experiment for real, we almost certainly will not achieve the predicted quantum value, okay, because the noise in our experiment is going to lower our value back down toward the classical one. But as long as we can achieve a value that is bounded above the classical value, then that is enough to rule out a classical explanation for this experiment. Okay, and that is exactly what happened in the Google supremacy experiment. So they say that they measured a value of b equals about 1.002. Okay, and so you'll notice that this is quite far from the ideal 2, but they were able to take enough samples to show that they were bounded above 1. Okay, and so now the question that interests us is, well, what are we to make of that? How hard is it to sort of spoof this classically, right? And even if we agreed that it seems kind of hard to classically spoof b equals 2, well, couldn't there be some fast classical method that would just get slightly above 1? So, okay, so we're going to address that question. But yeah? You.
Yeah, I was just trying to, your analogy to the Bell.
Yes.
I mean, classically, you're doing the right thing when you compare those two, right? So we don't know what the right thing classically is.
Well, of course, we don't know what is the best classical algorithm. So, I mean, that is a question that we're going to have to address. I mean, what in the case of, the Bell inequality was a theorem that we could prove, here it's going to rely on some unproved complexity conjecture. That is just the nature of the beast.
Yeah, I understand. I just was trying to understood that.
Okay, yeah.
You said b equals 1.
B equals 1 is what you would get with classical random sampling. We now need to explicitly address the obvious question of, is there a classical algorithm that would get better than b equals 1? Okay? So, okay, well, of course we don't know, right? Like if we suppose that p equals p space, for example, then surely there would be such an algorithm, right? Which is enough to demonstrate that any argument we give will have to depend on some unproved complexity assumption, and there is no possible way around that, no way of talking around it, anything. Okay, but there's a question of, well, what assumption, right? Now, it would be wonderful if, we could say, well, provided the polynomial hierarchy does not collapse or something like that, then no classical algorithm can beat b equals 1. Unfortunately, we do not know how to do that. Okay, and and this is maybe the first of the open problems or research directions that I will raise. Right, get better evidence for the hardness of spoofing the verification procedures in these quantum supremacy experiments. Okay, we, as Adam mentioned, it is a major open problem, even just to show that approximate sampling, or sampling a distribution that is close in variation distance to the target distribution. That if a classical computer could do that, then the polynomial hierarchy would collapse, right? And here I'm asking for something more stringent than that, because we want to rule out any classical algorithm that would spoof this linear cross-entropy benchmark, even if that algorithm might work in a completely different way than just sampling from the target distribution, right? You could imagine a classical algorithm that somehow just zeroes in on the S sub i's that maximize this, this score, right? And that would, do a terrible job of sampling from the target distribution, but it would do great at passing this test, right? We want to say that even an algorithm like that, if it existed and was fast on a classical computer, that would have some unlikely complexity consequence. Okay, now let me mention what Sam Gunn and I were able to do very recently. Okay, so this was sort of an adaptation of some earlier work that Li-Ji Chen and I did. Sam Gunn is an undergrad at UT, and he and I just gave a hardness reduction that is sort of specific to the linear cross-entropy test that Google actually applied. And so here's what we can say, okay? Let's say that you are given as input a random quantum circuit C, from some ensemble like Google's. Okay, and you now have the task of estimating the probability of a specific output string. I might as well say, for simplicity, the final probability of the all zero string. So, we start with the all zero string, we apply the circuit, we measure all our qubits in the 0, 1 basis, and we just ask, what is the probability of getting back the all zero string? Okay, so of course this is a random variable, if you like, as I vary over, the circuit C. The expectation of this random variable is what, anyone? Well, it's, there's 2 to the n probabilities, and by symmetry, they'll all have an expectation of 2 to the minus n. Okay, so you might say the trivial estimator for this probability will just be the one that always outputs 2 to the minus n. Okay, now let me make a bold conjecture. Okay, and this is where I'm going to stick my neck out. Okay. The conjecture will say that no polynomial time classical algorithm is able to achieve variance that is like significantly better than this trivial estimator. So basically, in classical polynomial time, you can get almost no insight into the probability of this random quantum circuit outputting the all zero string. Okay, and to be more precise, the variance of any classical polynomial time estimator, I'm going to conjecture that it cannot even be like this much better than the variance of the trivial estimator. Like it can't even be 1 over exponential in n being the number of qubits better than the trivial estimator. Okay, this is where I'm sticking my neck out. Now, just to calibrate you, okay, it is possible to do slightly better than the trivial estimator, and a neat trick for doing that is to use the Feynman path integral, right? Or what I'll call it that for physicists, for computer scientists, be the proof that BQP is contained in PP. Okay, these are two different names for the same thing, but I could take take a probability like this one, and I can write it as a sum of exponentially many contributions. Okay, and I can then, if I want to just estimate this probability, just very, very weakly, just slightly better than chance, I could always just sample a few random terms in that exponential sum, right? That gives me this probability. And what will I get that way? It's instructive to work it out. What I'll get is an estimator that does this better, this much better than the trivial estimator. So like 1 over x of m, where m is the number of gates in the circuit.
Is it n times m if you're running gates in parallel?
Well, okay. I mean, in that case, I would say it's the number of qubits times the depth or something. But it's really just the number of gates, the total number of gates in the circuit.
It seems like you could pick up amplitudes that are less than 1 from every single local gate, right?
Yeah. But no, but it's really just the number of gates, right? Each gate, like you multiply it out. Okay. So it is actually important for us that m is large compared to n. Right now, in the case of Google's experiment, let's say n is 53, m is on the order of 1,000. Okay, the gap between those two numbers actually matters, and as a further interesting point, this type of conjecture that we're making, I think that it is plausibly true for random quantum circuits. It is not true for boson sampling. Okay, it is not true for the IQP, the Bremner, Joseph, and Shepard model. Okay, in those models, there is sort of not an analog of m. There's not a notion of a number of gates that you just sort of sets your hardness and that you can just vary independently of n. Okay, so we are actually using the fact that Google built a chip that does in principle universal quantum computation. Right, it's not just a thing like boson sampling. Okay, so our whole conjecture is that in classical polynomial time, yes, you can get this bias in an estimator of a probability, but you're not going to get this kind of bias. Okay, now let me hand wave to you that if you accept that conjecture, then it follows that there is no classical polynomial time algorithm that can spoof Google's linear cross-entropy benchmark. Okay, and even by getting b that is slightly greater than 1. Okay, so the hardness reduction is like an extremely simple one. Like once I've posed the question, I could just give this as like a homework exercise for people here. But all we do is we say, well, okay, so suppose that I had a fast classical algorithm for spoofing this cross-entropy benchmark, right? So for generating samples with a large value of this sum. Now I want to use it somehow to get an estimator for this problem. So the first thing I will do is I'll have to sort of randomly permute my circuit in such a way as to hide which final amplitude I care about. Okay, so I could just like insert some random NOT gates at the output layer in order to get a new circuit, C prime, where the thing that I will care about is actually the final amplitude of some random other string, Z, right? And this is just so, because if my algorithm knew that I cared about the all zero string, then it could just corrupt the estimate for that string only, okay? I want it to be a random string. Okay, And now what I'll do is I'll simply, on my modified circuit, C prime, I will run my assumed fast classical algorithm for spoofing the linear cross-entropy benchmark. Okay, that will generate, that algorithm, when I run it, will generate some samples, say S1 up to Sk. And now I will simply ask the question, is Z, the output that I care about, among those samples or not? Okay? And now, if Z is among those samples, then that gives me some very, very weak statistical evidence that maybe this probability was a little bit larger than average. Right? Just, some very, conversely, if Z was not among those samples, that gives me some very weak evidence that that probability maybe was slightly smaller than average. Okay, this is a really poor estimation algorithm, but it will achieve, if you calculate it, it will achieve a bias over the trivial estimator that looks like this. Okay, which is good enough to refute that hardness assumption. Okay, so yeah, Adam.
So are you implicitly assuming that B is held constant as you?
Oh, yeah. So good. So there is a trade-off here. What I just said will actually work for like let's say any constant B that is bounded above 1, and it will even work for some B that is like 1 plus 1 over n, things like that. You can even get closer to 1 here. Okay. So a couple points to make. We haven't done much, but what we've done is we've said that there is nothing like super special about spoofing this benchmark that Google is applying, right? That if you could do that, then actually you would just get a handle into just the general problem of estimating output amplitudes in random quantum circuits, right? So the two things are connected, and indeed, well, I'm going to discuss this shortly. But the actual examples we've seen of algorithms for simulating quantum supremacy experiments are not tailored to spoofing these benchmarks, right? They really do just basically brute force the simulation of the entire quantum circuit. Okay, and so we're giving some evidence that is inherent, right? That is necessary here. Okay. The other point I wanted to make is that the noise in the circuit, in some sense, the only role that the noise played was to decrease the value of B that was achieved in the experiment. Okay, and so I'm stressing this because people constantly object that well, how do you know, even if a noiseless experiment would be hard to simulate, don't you need to know the exact details of the noise in Google's device, and couldn't, the specific, nature of the noise, couldn't it screw you up? And the answer is no, it doesn't, right? All that the noise does is it decreases the B value that you achieve. It means that you are violating this complexity theoretic Bell inequality by a smaller amount, okay? But, the hardness assumptions that we have, can talk about the hardness of violating the complexity theoretic Bell inequality by any amount, right? And so you just have to violate it by enough that you can detect that. And then, the further details of the noise model, just do not enter into the analysis. Okay, so maybe the sort of number one open problem, you could say, is just get better evidence than this for the classical hardness of spoofing a quantum supremacy experiment. I would love to know if we could make a weaker conjecture than this. Can one go in the other direction? Can one say that if one could had a non-trivial estimator here, then one could spoof the linear cross-entropy benchmark? I don't know how to go in that direction. I think that's a really nice open problem. But now, there's the eraser. course, it behooves us to look at the opposite direction and say, well, could we design better classical algorithms for simulating random quantum circuits or arbitrary quantum circuits? And that seems like an incredibly basic question, that would have been studied to death in the 90s or something. So, I guess it was partly, nice, but also partly disconcerting that, when we looked at it over the last few years, we discovered new things about this question. And so let me just make a little table of some of the main algorithms that you might think of for simulating a quantum circuit on a classical computer. And what trade-offs do they have? Okay, so the most naive way to simulate a quantum circuit classically would be with what I'll call the Schrodinger simulation, which would simply write out the entire wave function, the entire quantum state explicitly in memory, and then just keep updating it. Okay, so this is basically going to be about 2 to the n time and also about 2 to the n memory. Okay, and this would correspond to, let's say, the proof that BQP is contained in X. Exponential time. Now, to mention in the response by IBM to Google's paper, where they said that they could simulate Google's supremacy experiment in only a few days rather than in 10,000 years, using a Summit at Oak Ridge National Lab, which is the largest supercomputer that currently exists on Earth. They were just talking about doing this completely naive Schrodinger simulation, and what would they haven't actually done it. It's not so easy to get time on that machine, okay? But what would make it work according to their paper is simply that Summit has 250 petabytes of hard disk space, okay? And that is enough, just barely enough, but that is enough to store 2 to the 53 complex numbers, which is about 9 quadrillion of them. Okay, and then you just do this, brute force Schrodinger simulation. Okay. Now, a different approach, one that I already touched on, would be the Feynman simulation. Okay, this is a much more a memory efficient solution where you would just take the amplitude that the output amplitude that you cared about and just write it as a sum of exponentially many contributions, and then just sum up all those contributions, reusing the same memory for each one. So this uses only linear memory. The time is the real issue here. The time ends up being exponential in m, the number of gates. Okay, and even Google cannot do x of 1,000. It exceeds a Google, one might say. Okay. So just staring at this, an obvious question one could ask is there a way to interpolate and sort of get the best of both worlds here? That sort of surprisingly was not really looked at, but so Li-Ji Chen and I a few years ago proposed a hybrid algorithm, which is really just, if any of you know Savage's theorem in complexity theory, it's really basically just that. So the way it would work is that you take some amplitude that I care about, like going from x to y, and then I take my circuit C and I cut it into 2 halves. Let's say 2 equal-sized pieces, call them C1 and C2. And then I can always take an amplitude like this, and I can rewrite it as x C1 Z, and then Z C2 Y, right, like that. Okay, and then I can I can write an amplitude I care about as a sum of products of amplitudes involving shallower circuits, and then I can recurse. Right, I can recursively evaluate each of these amplitudes in the same way. And if you work out the recurrence relation, what you get is that this ends up using linear memory and time that grows like d to the n, where d is the depth of the circuit. Okay, so depth to the number of qubits. So it's not, it's not quite as good as this. Okay, but now this is actually now used in some of the state-of-the-art simulations of quantum circuits that IBM and Google and others have done. Okay. Now, what else is out there? Okay, what other classical algorithms are there for simulating quantum circuits? So, another major thing to pay attention to are tensor network contraction methods. These typically work best when the depth of the circuit is small. Okay, so these also have a dependence on depth. I don't have time to go into them, but it's interesting that Google actually made some engineering decisions, in building its Sycamore chip, such as, the choice of what kinds of 2-qubit gate they had, purely in order to try to evade tensor network simulations of their chip. Yes?
Are these all tensor network contraction methods?
I suppose that you could view them in that way, yeah. But there are let's say there are tensor network methods that sort of make very explicit use of the spatial locality and the low depth of the circuit. So that's kind of what I meant here. But yeah, this is a general framework that you could also slot these other things in. Fine. Okay. And then so the fear is, well, what else could be out there? Could there be algorithms that work for just approximating the output distribution of a random quantum circuit, even if they don't get it exactly? And so here, the very recent work by Knapp et al., which Adam also mentioned, I found to be extremely striking. And so what they say is, they don't have a rigorous proof of this, but heuristically, they can take a two-dimensional spatially local quantum circuit of constant depth, and they can approximately simulate it in what looks like classical polynomial time, approximately simulate its output distribution. Okay. Now this does not, conflict. This does not refute the Google result, because it only works for very small depth. Now, for what depth exactly does it work? Well, they're not completely sure. And maybe the most striking thing about their result is that they say that there is a phase transition in depth. So once you go beyond the phase transition, then their algorithm just completely fails. They don't know exactly where the phase transition happens. They say at any rate, with qubits, they expect it to happen well before a depth of 20. Okay, but this is an indication of what else might be out there that we have missed. So Boaz Barak has suggested to me the conjecture, which I think is very plausible, that there might be an efficient classical algorithm that would spoof the linear cross-entropy benchmark, in the case where the depth of the circuit is small enough. So it might achieve a value of b that is, for example, 1 plus 1 over exponential in the depth, or something like that. Maybe even 1 plus 1 over double exponential in the depth. Okay, but one can even write down algorithms that look like they would plausibly achieve something like this. Okay, but there remains a great difficulty in analyzing them. So I think that such things are certainly possible, and they should be investigated. Even if the Google experiment is already sort of outside of the range where this is directly relevant, we should know where the border is between simulability and not. Okay. So now, so that was my second question. Okay, now my third question. This is something that that Adam also touched on, but I think one of the biggest theoretical open problems for this area right now is to figure out, is there a way of doing a quantum supremacy experiment on a near-term device, which probably means some kind of sampling-based experiment, but in such a way where in order to verify the results with a classical computer, you do not have to do a 2 to the n time classical computation. Okay, so where the classical verification is efficient, and I think this is an immensely important problem. Okay, because right now, Google actually did not directly verify its hardest circuits. It's 53 qubit and depth 20. They relied on extrapolations from easier cases. That you could find plausible or not. But I mean, they went beyond. They went all the way up to the limit of what they could simulate with their 1 million core supercomputer that they had access to. Running for like a month, and then they went beyond that point. Okay, now one of the immense ironies of the IBM rebuttal paper is that if IBM can indeed simulate Google's device using the Summit supercomputer, then they should also be able to verify Google's hardest results, and which would be extremely useful for them, right? In a regime where Google had not known how to do that. Okay, but it's clear that with these, as long as the verification is done by brute force, 2 to the n classical computation, then you're sort of limited to, let's say, 50 qubits, 60 qubits. You're never going to verify something involving 100 qubits or 200 qubits. Okay, so I think that this is a huge question, and now let's talk about what is known about it. So of course, if we had a full fault-tolerant, scalable quantum computer, then we have some excellent solutions to this problem already. Okay, the classic, you could say, one of the golden oldie of quantum supremacy experiments would be Run-Shor's algorithm. Factor a huge number, and that has the advantage that, of course, a skeptic can just very, very quickly check the claimed prime factors for itself. Alternatively, if you don't like factoring, we now know that you can take any problem in BQP, any quantum computation whatsoever, and under suitable cryptographic assumptions, there is an interactive protocol where the quantum computer will, receive challenges from a classical verifier, send back answers, and where it will actually prove that it executed the quantum computation correctly. This was the breakthrough result of Irmila Mahadev. Okay. Unfortunately, both of these seem like they require a fault-tolerant quantum computer, or at least something approaching one. Okay, so we still have the problem of what are we going to do? Let's say in the next 5 to 10 years in the in what John Preskill calls the NISQ era, the noisy intermediate scale era, and. So, a couple things that I could mention. There was a beautiful proposal by Mick Bremner and Dan Shepard. Which involved their IQP model. They're also called the commuting Hamiltonians model. And they gave a proposal for, here is a way that the verifier could generate a random circuit But while they do this, they secretly, remember some trapdoor information about this circuit. Okay, they remember something about how they generated it. So let's say the verifier is generating a circuit C sub k that depends on some secret string k, which the verifier will keep. Okay, now this goes to the quantum computer. The quantum computer now sends back samples from the output distribution of this C sub k, S1, S2, and so forth. And then in their protocol, the classical computer would be able to use its string k in order to actually efficiently check these samples. Okay, to check, are they clustered in some secret way that depends on k. Okay, now the way that this worked was complicated. It involved some very specific error correcting codes. I never really understood it, but I spent 10 years trying to get people more interested in this, in trying to see is this secure, is this not secure? Because this is exactly the kind of thing that we would need. And then a month ago, I was giving a talk and mentioning that people should really spend more effort on this. While I was giving that talk, actually a paper appeared on the archive by Greg Kahanu-Hoku-Meyer, is that the name, here at Berkeley, and this breaks the protocol. So so we now know that this is insecure, and so now all the more so this is an open problem. Design some interactive protocol, for example, for boson sampling or for random circuit sampling. Design a way to generate a circuit, that can be applied by a near-term device, but in such a way that this circuit will have exponentially many possible outputs. But you, the person who generated the circuit, will know some secret that will let you recognize the outputs that are coming as, yes, these are the ones that I was looking for. Okay? I think that this is a wonderful challenge. Now, we did spend some time thinking about this in the context of boson sampling. And so you might say that a dream, like if life smiled on us maximally, right? Then maybe what you could do is with boson sampling, for example, you could generate a linear optical network where there is one particular output, so one particular collection of numbers of photons in each of the output ports, call it S, where that output would just have a really, really large probability. By really, really large, I mean like 1 over polynomial in n being the number of photons. Okay, and you, as you generated the linear optical network, you would know S. You would generate it along with knowledge of that, of this, enormously likely output. Okay, now a classical person who was just looking at the linear optical network would have no clue what S was. Okay, it would just look like a big mess to them. But if you actually ran the experiment, sent the n photons through the linear optical network, then a quantum computer would be able to show that, yes, it is getting S an appreciable fraction of the time. And in this way, you could verify that the boson sampling experiment was doing the right thing. Okay, that would be great. Unfortunately, there is a result which I did with the mathematician Hui Wen in 2014, and which was then built on by Berkowitz and Devlin in 2016. And what it basically shows is that this dream is unachievable for boson sampling. Okay, so what we can show is that if you have a if you have a matrix, let's call it A, and its norm is at most 1, so it can be embedded into a unitary matrix. And also, its permanent is sort of appreciably large, like 1 over a polynomial in n. A is here in an n by n matrix, complex numbers. Then A must be sort of highly degenerate in some sense, which one could formalize by saying that most of the rows of A will be dominated by a single large entry. Okay? Or to put it differently, if I try to construct an optical network that has this secretly high probability output, that output will stick out like a sore thumb in my in my description of the linear optical network, right? A classical person will be able to find it, very easily. Okay, so, but now this does not rule out that some interactive protocol could be done for boson sampling. It would just have to involve many, like let's say exponentially many possible outputs that you can all recognize, rather than only 1 or 2 outputs. Okay, and I view this as a major challenge for the field, whether for boson sampling, for random circuit sampling, whatever, to find such a protocol. Okay, so now my last thing that I wanted to mention is to find actual applications of random circuit sampling. Okay, and until recently, I think this would have sounded like an oxymoron, right? Like this is a task that is almost specifically designed to have no applications, except for disproving Gil-Colli and so forth. But a couple of years ago, I made an observation, which was that once you can do random circuit sampling, in the way that Google, looks like it is now done, then you can almost immediately take the experiment, take the random circuit sampling experiment, and you can repurpose it as a way to generate cryptographically certified random bits. Okay, so basically we're just looking at this setup where this challenger sends a circuit to a quantum computer. The quantum computer quickly sends back samples, and we're just sort of looking at it from a different lens. And we're saying, well, the quantum computer has to quickly respond with samples that pass this linear cross-entropy benchmark, right? Now, the original purpose of that was in order for the quantum computer to prove to the skeptic that it really is a quantum computer. Right. And we think that this is a good test for that. But if the test passes, then in some sense, it is proving something else as a byproduct. Or let me try to just convince you that at least intuitively that this is true. Even a quantum computer, suppose that it had to pass this linear cross-entropy benchmark, but do so in a way that was secretly deterministic. Okay, how would it do that? Right? Well, it could find the, maybe the highest probability output. But the thing is, we don't expect that even a quantum computer could efficiently do that. Okay, so, intuitively, it looks like what the quantum computer would have to do is sample the output. Now it can play a few games here and there. Like it could keep sampling until it finds a string whose first bit is a 1. Right? So it doesn't have to sample from exactly the distribution we want. But, no matter what it does, it seems like it has to sample from some distribution that has a large entropy. Okay, and therefore, if the test passes, then it could only have been passed by a way that generates a lot of randomness. Now, by making some stronger complexity theoretic assumption, one can justify what I just said. One can say that if it could do it in a secretly deterministic way, then there would be some like AM protocols that we don't think exist. Okay, but there are many open problems here, related to can you make this an actually practical protocol, right? Like, the verifier needs some randomness even to generate the circuit. Can we generate it pseudo-randomly using a small seed? Why should everyone else trust the verifier? Can we get a decent bit rate out? We can get some random bits out, but can we get more? Can we get more and more random bits by using the same circuit over and over? rather than by having to repeatedly generate new circuits. And finally, what other applications are there for random circuit sampling? There might be other, this could be used for like proof of stake cryptocurrencies, for example, where you need a large source of public randomness. Are there other cryptographic applications where a random circuit sampling experiment where its sort of result proves something cryptographically useful to you? Okay, so this is something that is really exciting me right now as one of the main possible applications for quantum computers in the next decade, let's say. All right, and let me just leave you with one kind of Zen question to contemplate. All right, so I said that quantum supremacy experiments are basically the complexity analog of the Bell inequality. Okay, so how many of you know Aaronson inequality, right? That says that quantum computers cannot even a quantum mechanics, you can only violate the Bell inequality by so much and by no more. Okay, so what is the complexity version of Aaronson inequality? Can a quantum computer achieve a B value that is greater than 2? If you had a magic box that could achieve B equals 3, would that be computationally useful? Would that let you solve any problems that are outside of BQP or that are hard even for quantum computers? So let me just leave you with that thought, and thank you for listening.